Hello everyone, my name is Michael Tuis, and I'm here to tell you about an exciting research project in solar energy right now. And in order to help me tell this story, I've invited a really good friend of mine, Marcel, the solar cell. You see, Marcel and I work really closely on this project because he's one of the solar panels that we test as part of this experiment. And his dream in life is to become the very best solar panel that nobody ever was. And he has a special little skill in order to help him do that, called a polyethylene backsheet. This is a material that promises to protect solar panels and their components, but also to basically increase the lifespan and overall performance of these solar panels beyond anything that's currently on the market. The only problem with them is that we don't actually know if they really do that. So what Marcel has decided to do is that Marcel decided to hop on a plane from his European home, fly across the Atlantic in order to prove himself to the world. He arrived at our little Colorado lab to basically demonstrate his skills, right? And in order to do that, he signed up for something that we like to call the Gauntlet. The Gauntlet is a series of experiments of accelerated weathering conditions where we subject solar panels to their worst day every single day. Basically, the harshest UV conditions, the harshest heat, and the harshest humidity that they might experience on any place on Earth. And we do this in order to basically simulate years of wear and tear in just a few months. And basically, we're trying to understand how are these going to survive 20 years from now, 10 years from now, after we install them. And yeah, so Marcel joined this gauntlet. This is him in the gauntlet with a couple of his colleagues, all going head to head to prove that they really are the best solar panels for the job. And some of them aren't going to make it. Some of them are going to crack under the pressure. But some of them, maybe Marcel, are going to prove that they are truly the stars of the show and win the gauntlet and show that they really are the best performing materials for the job. Now, Marcel's story is the story of our research, right? This is its title. It's a lot of sciencey words that you don't need to know. Basically, we just call it backflip. And it is a multinational, multi-lab collaboration with tons of different collaborators and researchers on this project to try and find the best materials to increase the lifespan and reliability of solar energy. This is what we're all about. Because, reliability maybe not be as flashy as something like performance or efficiency, new quantum materials and semiconductors and all that stuff, but it's a critically important part of solar energy. Because what we see solar energy as is we see it like a boxing match, right? Yeah, it's really nice to have a high power solar panel, a high efficiency solar panel, really have a lot of power in your punch, but if you can't take a punch, you're not going to make it far in boxing. You're not going to make it past round 1. What we really care about is how do these solar panels fight in round 5, and round 6, round 7, and beyond. So, we want to know what's going to happen in the long term, and we want to make fighters who can last in those later rounds. And in order to do that, we need to understand how are they fighting? What are the effective techniques that allow them to roll with the punches? Well, to help us with that, here's my other friend, Jimmy the solar cell. See, Jimmy, he wasn't able to roll with punches, and he kind of fell out of the gauntlet. But he gives us really good insight into how solar panels fail and how they fall out of the ring. And one of the first things that Jimmy had was Jimmy started to experience electrical failure, shorts, and things within his circuitry that meant that he wasn't really performing like he used to, and eventually started to fail. And why did he start experiencing these shorts? Well, he literally cracked under the pressure. This is cracking that we see when we look at Jimmy as a fighter. And what this means is that allows water and things like that to get into the circuitry and start to cause it to fail. It also presents a really bad safety risk because, fun fact, humans and exposed electrical equipment don't really mix very well. So that's a grave concern when we're talking about people who work on solar panels, maintain them, and install them. And so we care about that very much. Now, the other thing we really care about is discoloration, because one of the major signs of degradation of these materials is that they start to yellow. And, which is great from a scientific perspective to see oh, that's how much something is degraded by. But it's also great from a design and aesthetic perspective, right? If you're putting some really nice, clean solar panels on your roof, if they start going yellow and falling apart, you may not appreciate that. So this is something we care about from a consumer perspective. Now, kind of thinking about how they fail and looking at the techniques of all our different materials, you might wonder, who is the best fighter? Who is the best material for the job? Well, the answer, like many things in life, is it depends. And the reason it depends is because some solar panels are better in some environments than others, right? One solar panel might be really good on a high altitude desert, but may fail very quickly if you put them in swampy Florida in hot, humid weather, you know? So fundamentally, it depends. And this kind of comes up to, it's almost like putting a boxer in an MMA fight. Maybe they'll do well, but the MMA fighter might just beat them. So what we're caring about is we're also trying to see who are the boxers and who are the MMA fighters. What climates do these materials perform best in? And how can we learn from those lessons to basically improve them everywhere? And to give a bit of an idea, let's just look at how some of our fighters fought. These are some of our materials. The backsheet 1 and 2 are the polyethylene some of our polyethylene materials. And backsheets 4 and 6 are some of the conventional solar panel materials that you see out in the field today. These might be on your house right now. And as you can see, some of them cracked under the pressure. Backsheet 2, for example, started to crack under the high heat and humidity, and backsheet 4 and 6 really got stripped away and started discoloring and falling apart under the high humidity. And if you look at backsheet 4 and 6 in the high UV exposure under the sun, they start cracking and falling apart really quickly. This is just exposure in the gauntlet, right? Meanwhile, one of backsheet 1, Marcel in this case, is one of our polyethylene materials, and basically just shook it off. Didn't affect him at all. But so yeah, just looking at our fighters, we get a decent idea of how well they're performing. But just like anything, just looking at something doesn't give you the full picture. What you really care about is performance, right? How well did they fight? Well, luckily, we look at that too. What we care about in solar energy is energy production, is power production. And this is a graph that basically is culminating thousands of different data points from this experiment into a single graph to show you how well each of these materials are performing. And basically, as you can see, our backsheet 1 and 2, which are our polyethylene materials, have a much higher power output overall in all these different test conditions. Each one of these lines is a different climate, basically, than all our solar panels, which is really exciting. Some of our conventional materials do perform better in certain climates, but overall they have a lower performance. And to give an idea of how much lower, right? If we take one of our lowest performing materials in the climate and one of our highest performing, which is our polyethylene, we're talking about a 7% difference in overall performance over the lifetime. That's pretty big, right? That's pretty significant. And it's incredibly significant when we talk about this isn't just an isolated experiment. The point of this is to learn lessons to teach to the next generation. Marcel is going to take the lessons he learned from the gauntlet, those fighting techniques, and he's going to teach the next generation how to become better fighters, to become better solar cells. And fundamentally, this is not a lesson just to teach them how to win a single fight or to win a single matchup. We're mobilizing for war. There's no other realistic comparison of how large solar energy is right now and how big of a scale this fight is. Because if you look at the expansion of solar energy in the last 2 decades, it is massive. The last decade alone, we've seen a massive expansion to the point where in 2019, 117 gigawatts of solar energy was installed across the world. Now, gigawatts, it's not really a unit that most people are familiar with, so let's put that in perspective a little bit. That is the equivalent of 365 million new solar panels being installed. Let that sink in. 365 million. And to give a little bit more perspective on how massive that number is, that is enough to power 35 million homes, and it takes up about the same square area as 2 Californias. And so if we can improve this overall performance by 7% by just choosing the different materials and different fighting techniques, that is huge, right? Let that sink in. That is huge. So hopefully, we can not only look at how we can continue to fight and expand solar energy and make it a cheap, viable energy option that reduces all our energy costs, but we also should look at how we fight, because how we fight matters. And if we want to make this as effective as a mobilization as possible, we need to pay attention to that. I'd like to thank you very much for listening, and have a good rest of your day.